Hello, I welcome all of you to my chemistry YouTube channel. Myself, Dr. Atul Nagpure, Assistant Professor. Today our topic is valence bond theory. In order to explain the nature of chemical bonding in complexes, various scientists has put forward their own theories. Amongst these, valence bond theory, crystal field theory, ligand field theory and molecular orbital theory. This theory was successful in explaining the characteristics of coordination compound. Today we'll try to discuss the valence bond theory, which is given by Linus Pauling. According to valence bond theory, metal atom or metal ion makes available empty atomic orbital, which is equal to the coordination number of the metal in a complex. Afterwards, these empty atomic orbital of the metal undergoes process of hybridization in order to give the equal number of hybrid orbital which has the nearly same symmetry and equivalent energy. And these hybrid orbital will try to arrange themselves in the space and which will give the exact geometry. Afterwards, these hybrid orbital of the metal react with the field ligand atomic orbital, and that's how they start to form a coordinate bond. A coordinate bond is a special kind of covalent bond in which the ligand molecule or ligand ion donate the 2 electron, and because the orbitals of metals are empty. Afterwards, the form coordinate bond between metal and ligand will have the characteristics feature of atomic orbitals of metal as well as the ligand. Importantly, this coordinate bond has the polar nature because the mode in which they form. So Linus Pauling was trying to explain the bonding in various complexes because earlier days there was not much more theory which could address the geometry, the nature of metal ligand bond and magnetic nature. The Pauling was able to successfully explain all the characteristics in the complexes, and this theory will try to address it. Now here you can see I am trying to explain a coordination number 2, 3, 4, 5 and 6. Not only these coordination number, we can have 7, 8, 9 and so on, but our today's lecture will be focuses for the complexes which have the coordination number between 2 and 6. So let's start our discussion. A coordination number 2, when coordination number 2 is there, the metal ion will be have hybridization sp. Sp, when S has 1 orbital and p, it can be px, py or the pj. Okay, so when I am discussing a coordination number 2, we require 2 orbitals of the metal. Here will be 1s and 1p. Now here you can look at the geometry of the complex. You can see very carefully here. Now M is the central metal ion or central metal atom, and these two are the ligand molecule. So if I keep the molecule in this fashion, I have a linear geometry or diagonal geometry in which this angle between this is a 180 angle. Now let's discuss this copper complex, this CuCl2 complex. This is a CuCl2 complex, shows the sp hybridization in which the copper, now you can see the copper has the +1 charge, and hence this is a 3D 10 system, right? So afterwards this copper now will use its 4s orbital and one of the 4p atomic orbital. So I'm writing here a 4s and 4p. Now these two orbital, these 1s and 1p, now will undergo the sp hybridization, right? Will give the two hybrid orbital. Now they can arrange in this way, and afterwards the ligand or field orbital now will going to react with this. So because these are empty. Now suppose the ligand molecule approaches to this orbital. Now you can write that this is a 2 electron and this is the electron. Now these two electrons are given by Cl minus ligand. So I am just showing that both the electrons are given by the Cl minus ligand. The detailed description we will see in the various video which I am going to make for each coordination number. But in this lecture, just try to see what are the coordination number and the geometries are possible for this one. So if I am having sp hybridization, as I showed you, that two ligands molecule will arrange in a diagonal fashion and angle between them will be the 180. In this case, copper +1 have a 3D 10 system, and 4s and 4p orbital will use to give the sp hybrid orbital. Now they will react with the field chloride ligand orbital. Now they going to give this kind of complexes. Similarly, if I now take a coordination number 3, it is sp2 hybridization, and in this case the ligand molecule will arrange themselves in a triangular planar mode. So you can see here, this is the way I can show you. Let's consider this is my central metal ion, and these are the ligand, 3 ligands are there, and they are in the trigonal planar kind of geometry. And if I take the angle between these two will be how 120, 120 and 120. So because overall will be 360, and between two successive ligand angle is 120. And here the example is a mercury complex in which iodine is the ligand molecule. Let's move towards coordination number 4. Now one important point all of you has to keep in the mind. When we have coordination number 4, two types of geometries are possible. One is tetrahedral and one is square planar. Now I am going to show you the geometries of this one. So this is called as a tetrahedral geometry, right? And this is called as a square planar. You can look at in this angle also. All are in a square planar mode, and here is the tetrahedral fashion. So first, when we have sp3 hybridization, remember that geometry will be always tetrahedral. In this I have given one example of the nickel complex, and we have chloride ion is a ligand, and nickel +2 is a 3D8 system. If I take again same coordination number, importantly the hybridization of the square planar geometry may be one of these. One is dsp2 and second is sp2d. Remember that when we have a square planar geometry, the d orbital involved in the hybridization will be always dx square minus y square. We have 5d orbital dxy, dyz, dxz, dz square, d square minus y square. So when we have square planar kind of geometry, in this geometry the d orbital will be always d square minus y square. Why this is the orbital, that part we'll discuss in crystal field theory. But for time being, remember square planar means d square minus y square. This is the orbital involved in the bonding. Here again sp2d, a kind of hybridization mostly shown by copper plus 2 ion. Please, you can make a note of this also. When we have a copper plus 2 ion, and when we have copper plus 2 ion, and you know the copper plus 2 ion is having 3D and 9 system, and if you have coordination number 4, if you have coordination number 4, you can say here ML4 kind of complexes, and here M, if I am having M is a copper plus 2, these kind of complexes always shows sp2d hybridization. This is a very important point. Whereas platinum plus 2, nickel plus 2, palladium plus 2 always exhibit dsp2 hybridization. However, the copper plus 2 with coordination number 4 always exhibit sp2d hybridization. So in the coordination number 4, we have seen the two different hybridization, sp3 tetrahedral, dsp2 or sp2d is a square planar complex. Now if you look at here in this kind of square planar, if I take in this way, total is 360, right? And I have 4 ligand. So if I take the angle between these two will be the 90 angle. So I'm going to say angle between these two ligand or these two ligand will be 90 angle. 90 angle here, 90 angle here, 90 angle here, 90 angle here. Okay. So coordination number 4, there are two types of geometries are possible, tetrahedral, and now we have the square plane. Similarly, for coordination number 5, here 5 you can look at very carefully. For 5, a trigonal bipyramidal, one geometry which has dsp3 hybridization, and for coordination number 5 we have a square pyramidal kind of geometry. Okay. Now I am just going to show you the structure of these molecule. So look at this first one. This is a trigonal bipyramidal. This is trigonal bipyramidal in which we have this 3 ligand, 1, 2 and 3rd ligand are actually in the one plane. I can say in kind of triangular plane, and one ligand is above the plane and one ligand is below the plane. Okay, so these kinds of geometry is known as a trigonal bipyramidal geometry. And if you have trigonal bipyramidal geometry, the d orbital involved in the bonding will be always dz square. Pentacarbonyl iron 0 generally shows these kind of complexes. I'm going to discuss a bit of this. Let's say we have iron complex here, FeCO by 5. Now since carbonyl is a neutral ligand, the charge on the iron will be 0. Okay. Now since CO is also strong field ligand, the electron in the 4s orbital now will shift it to d orbital. Now finally become 3d8 and 4s 0. Okay. So now this dh, 1d is empty. So if I write down here, this is my d orbital. Okay. And this is now 4s, and if I write down here 4p, I will label. So this is my 3d8, right? And this is my 4s, and this is the 4p. Detailed explanation I will give in the different lecture. Just try to understand here how the bonding occurs. 1, 2, 3, 4. These are the 8 electrons over. Now after that 1d, right? 1d 1s and 1, 2, 3p. So we have 1, 2, 3, 4, 5. Now these 5 orbitals will undergo dsp3 hybridization, and that's how this linkage will occur. One CO will give the 2 electron, so I can write a 2 star means for the 2 electron, and this is the way we need to explain the bonding. So when we have dsp3 hybridization, and if your trigonal bipyramidal geometry is there, the d orbital will be always dz squared. So this is the orbital what I have shown here. This has to be always dz squared. This is a very important point. Keep in the mind. And this is a structure of trigonal bipyramidal geometry. Now let's move towards second type, which is called as a square pyramidal. Okay. Examples I have given: pentachloro nickelate complex, and in which nickel is actually a +2 charge. So you can see here, I will show in this way. So 1, 2, 3, 4, these 4 ligands are in the square planar kind of mode, and one ligand is just above, and this coordinate side is empty. So total coordinates number 5, 1, 2, 3, 4, 5. Now interesting part here, when we have coordination number 5, I have 2 types of geometries are possible. This is a square pyramidal, and this is called trigonal bipyramidal. But which factor, like energy factor, forces, driving force, which favors either this one or this one, we'll discuss in a different video. But try to understand here. For coordination number 5, we have 2 types of geometries are possible. Trigonal bipyramidal, in which the d orbital is dz square, and when we have square pyramidal geometry, in that the d orbital will be always dx square minus y square, and this is the important point. I am just moving now for coordination number 6, and mostly if you are aware, coordination number 4 and coordination number 6 are the 2 most important and occurs in the coordination chemistry, because coordination number 2, 3 and 5 are the rare complexes. So if I am having a coordination number 6, this is the octahedral geometry. 1, 2, 3, 4 are in the square planar fashion, and 1 is just above and 1 is below to the plane. And here again we have 2 types of geometries are possible. One is sp3d2 and second is d2sp3. Moreover, this sp3d2 is also known as outer orbital octahedral complexes, because the d orbital is outer, right? And if you have d2sp3 hybridization, this d will be inner, and hence it is known as inner orbital octahedral complexes. And out of 5d orbital, the octahedral complexes will be always having dz square and dx square minus y square orbital involved in the bonding. So if I take this complex, iron Fe by6 minus the complex will show sp3d2 hybridization. On the other hand, this cobalt complex with cyano ligand having cobalt plus a charge will always going to show a d2sp3 kind of hybridization. That means you have to very much sure whether this is outer or this is the inner. Normally a weak field ligand shows sp3d2 hybridization, and a strong field ligand shows d2sp3 hybridization. This is what all about the hybridization. As I told you already, not only these, we can have coordination number 7, 8, 9 and so forth. Now let's look at this structure. So if I take the angle between these two, 1 and 2, if I take the angle between these two will be always 90. If I take, now this is called as a equatorial ligand, and this above and below are called as a axial ligand. So if I take angle between axial and equatorial will be always 90. Angle between equatorial, axial, now this and this 90, this and this will be again a 90. But if I take angle between this and this one, above and below will be always 180 angle. So in all the cases you must surely what is the coordination now number, what is the hybridization, how the bondings and the geometries occur, angle between these two. If I take linear, 180. If I take diagonal planar, 120. If I take square planar, I'll be having 90, and so on. So this lecture was just the introduction about the valence bond theory. In the next lecture, we will try to discuss each coordination number along with this example and detailed discussion regarding that. The discussion will going to involve the bonding, the hybridization and magnetic nature of the complexes. So I hope that you like this video. If you have any question, you can comment. Thanks for watching. Signing off.